Here is your long-awaited Section 3 video lecture entitled Counting Atoms. Let's start off with some definitions here. We have the atomic number, which is something that's on your periodic table, and it is equal to the number of protons in the nucleus of each atom of an element. This is the number of protons, therefore defines what element you're looking at. We have the mass number, which is the number of protons plus the number of neutrons of a single atom of an element. This is not an average. You're looking at one particular atom, and not an average. You're looking at an actual atom, and you're counting how many protons and neutrons are in that nucleus. We also have isotopes. Okay, isotopes is the definition we need to have under our belt. Isotopes are atoms of the same element, therefore have the same number of protons, but they have different masses because they have different numbers of neutrons. A nuclide is a general term for a specific isotope of an element. If you're referring to specific isotopes, you might hear that term used. When talking about isotopes, there are two different notations used. One is called hyphen notation, and one is called nuclear symbol notation. And let's look at both of these considering hydrogen and its three isotopes. So here we have hyphen notation. It's we're representing hydrogen here, so we have the atomic symbol for hydrogen, that capital H, and then a number next to it. Over here we have our second isotope, still the capital H, which represents hydrogen. But then we have a 2, and then last we have, again, capital H represents hydrogen, but it has a 3 after it. For the nuclear symbol, we again have the capital H representing hydrogen, but we have two numbers, one subscript, one superscript. Now, hydrogen has 3 different isotopes, one of which has no neutrons, one has 1 neutron, and then the last has 2 neutrons. The hyphen notation for protium, the form of hydrogen that has 1 proton but no neutrons, is represented in hyphen notation as capital H hyphen 1. And so the number after the atomic symbol is representing the mass number. It is the sum of the number of protons and neutrons. Here there's 1 proton but no neutrons, therefore the number is 1. For this second form of hydrogen deuterium, there is 1 proton and 1 neutron, therefore the sum of that those numbers is 2. So we have hydrogen, the atomic symbol for hydrogen, and then hyphen 2. Lastly, we have a form of hydrogen that has 1 proton still because it is hydrogen, but 2 neutrons. And so the mass number for this isotope is going to be 3. For the nuclear symbol notation, again, we have the atomic symbol for hydrogen, and we have both the atomic number and the mass number both being represented here. And as we move over to deuterium, we see that the atomic number is still 1 because that's the number of protons, and it shouldn't change because we're still talking about hydrogen. But the mass number changes because we have an extra neutron in this version of hydrogen, and so the mass number goes up to 2. And then in our third isotope of hydrogen, we have 2 neutrons, and so the sum of the protons and neutrons is 3. I'd like you to pause the video at this point so you can attempt to fill in this chart. Please pause the video now. Alright, here are your answers. Bam, there you go. If you'd like, go ahead and pause the video now so you can double check your answers, and if your answers did not match up with anything I have represented here, take a moment to stop and figure out where your calculations went awry, if it was simply a silly math mistake, or if your model for any of these columns is slightly incorrect. You can change that model. If you still can't figure it out after adjusting your model and seeing if that works out, you're going to need to bring this question to me during class. Some more definitions here. We have atomic mass unit, something that we've used in class already. It is defined as exactly 1/12 of the mass of a carbon-12 atom. We also have the average atomic mass, which is the weighted average of the atomic masses of the naturally occurring isotopes of that element. And so what that means is carbon has a few naturally occurring isotopes, and they have different mass numbers. And so what we want to do when we represent the average atomic mass of carbon, we don't want to have to ask the question, well, are we looking at carbon 12, carbon 13, carbon 14? What are we doing? So we do some calculations. We take into account how much of each isotope there is when taking into account the weighted average. So carbon, for example, the naturally occurring forms of carbon is mostly in the upper 90% carbon 12. Okay, there is some carbon 13 and carbon 14. However, those percentages are so small that they change the average. They affect the average of carbon, the average mass of carbon, very, very little. As you can see, the average atomic mass of carbon is reported as 12.01 AMU on your periodic table. An example of what we're doing when we're calculating the average atomic mass, take a physics classroom. We're going to take all of the physics books in that classroom, and we're going to get ourselves an average atomic mass of all of those books. So just using a regular old bathroom scale, we're going to weigh each of those physics books on their own, and then add them together. Once we have the sum of all the masses of those physics books, we're going to divide by the number of books we have, and in that way we're going to find the weight of the average textbook in that class. Okay. Now if we go over and into the chemistry classroom, and we do the same procedure for the chemistry books, and then maybe go over to the biology class and you carry out the same procedure for the biology books, we're going to have the mass of each of those individual science textbooks. Now, my guess is that the physics book is going to have a different mass than the chemistry books, and that's going to have a different mass from the biology books. Okay, but we are going to take that mass of each of those types of books, and we are going to take into account how many there are. Let's assume there's only 20 physics books, there are 50 chemistry books, and then there are 100 biology books. Because the biology books are so heavily represented, the average book mass is going to lean more towards the mass of the biology book. However, realize that the average mass that we're reporting here will not actually equal any of the textbooks, the actual masses of the textbooks that we're representing, or that we're actually measuring here, because it's just an average. Next is a really important idea. We need to be able to relate the mass of a sample to the number of atoms in that sample. One idea that we're going to continue to talk about for the rest of the year is the mole. It's the amount of a substance that contains the same number of particles as there are in 12 grams of carbon-12. And the idea is very similar to that of a dozen. It's an exact number, and it's defined. It's not going to change. It doesn't matter if you're looking at a mole of carbon, a mole of hydrogen, or a mole of calcium. You're going to have the same number of particles in that sample, because that's what a mole is. Now, Avogadro's number defines how many particles are in 1 mole. Okay, Avogadro's number is 6.022 times 10 to the 23rd power. So, and that represents how many particles are in 1 mole. So if I tell you that you have a mole of a particular object, that means that you have 602 hexillion of those objects. It's a very, very, very large number. Now, using that mole concept, we can try to mass 1 mole of any particular pure substance. We can take carbon, for example, and we can take the mass of 1 mole of a pure substance, and that would be the mass of that mole, the molar mass, and you have access to the molar mass of every element by looking at your periodic table. It's the average atomic mass, but we're just swapping those units out from AMUs to grams per mole. And you're going to be using this molar mass in conversions. Now, you can use the molar mass. Molar mass is most normally given in grams per mole. So that means that you're going to have grams as a numerator and moles as a denominator. But that doesn't mean you can't flip those around, as I have here. We have moles on the numerator and grams on the denominator. That's perfectly acceptable. And this sort of conversion factor is going to be put into place when you're converting from a particular mass in grams, and you're trying to convert to a number of moles. You can use the molar mass in the same way, but going from moles to grams by having grams on your numerator and moles in your denominator, because when moles are on your denominator, moles are going to be the thing that cancel out. So here's a couple examples converting between grams and moles. We're going to talk about helium in both of these examples, but in the first example, we're converting from moles to grams. In the second example, we're converting from grams to moles. So we have 2.00 moles of helium. And we want to find out how many grams of helium that is. Well, looking at the periodic table, we can see that helium, for 1 mole of helium, there is a mass of 4.00 grams. And so because we want to cancel the moles here, we need to have moles on the denominator and grams on the numerator. The only unit that will be left would be grams. This conversion factor, the way it's set up, lets me know that I need to carry out multiplication between the 2.00 and the 4.00, and then divide that by 1. My answer being 8.00. Again, the only unit I have left is grams of helium. Going the other way, from that 8.00 grams of helium, we can use the exact same conversion factor as in the first problem. We've just flipped the conversion upside down. Instead of 4.00 grams of helium over 1 mole, we're going 1 mole of helium over 4.00 grams of helium. Now, the way this conversion factor is set up, you can the math is telling you that you need to multiply 8.00 by 1 and then divide it all by 4.00, giving you an answer of 2 moles. Here's some examples of converting from moles to grams. Went too fast. We have 3 examples here. I have 4.57 moles of copper, and I want to figure out how many grams of copper I have. Now again, I know for sure I'm going to have moles on the bottom here because I need these moles to cancel out because I want my unit to be in grams when I'm done. On the numerator here, I'm simply going to pencil in the molar mass for copper, which is 63.55 grams over 1 mole. Notice the moles cancel. The only unit I have left on the numerator is grams, so that carries over. The way I've set up my conversion tells me that I need to multiply 4.57 by 63.55, divide by 1. I have an answer of 290. Now, your calculator is going to give you some more digits here, but notice this 4.57 tells me that I need to have 3 significant figures. So it's 290, and I'm going to include this decimal at the end of the number to make this last 0 significant. Second example, I have 12.3 moles of potassium. I'm going to set up in the exact same way. For my conversion factor, I'm going to use molar mass, moles being on the bottom because those need to cancel, grams being on the numerator, so that can be the unit I have at the end. Moles will cancel. The math tells me that I need to multiply 12.3 by 39.1 to result in 481. Down here, I have chosen to use this potassium twice, but also the number of moles that is equal to the 4.57 in the first example, because I want to illustrate something. So again, after I've set up my conversion here, 1 mole of potassium is 39.1 grams of potassium. Moles cancel, the unit being in grams left over. The math tells me that I need to multiply 4.57 and 39.1. My answer will be 179 grams of potassium. Now what I want to point out here is I have the same amount of atoms in my first and third example. And both examples I have 4.57 moles. The only difference is in my first example I have copper, and in my second example I have potassium. Notice I have the exact same number of particles, but copper has a larger molar mass than potassium. It's a more massive atom. And so the same number of particles, the same number of moles, is going to be expressed as a larger mass of copper and a smaller mass of potassium because each individual atom of copper is more massive than each individual atom of potassium. Now in the second and third examples, I use potassium for both, and I change the number of moles I have. Now 12.3 moles is more potassium than 4.57 moles. Now the molar mass is the same because it's potassium both times. We have 39.1 grams. Now I have somewhere around 3 times as much potassium in my second example as I do in my third example, and so the mass of that many more potassium atoms comes out to be a much larger mass. Okay, so I want to point that out as we try to get more intuitive with our calculations. Let me get those up here. All right, so here's some more examples. I'm using the exact same numbers in the exact same elements, but instead of going from moles to grams, I'm now converting from grams into moles, and I have messed up the notation on the answers. That should be moles, moles, moles for the answer. My apologies. I'm going to have to fix that. Go me. But here I have 4.57 grams of copper, and I'm going to still use the molar mass of copper, the 63.55 grams per 1 mole. However, in this situation, I need to cancel out grams, so I'm going to put that on the denominator. And so the only unit that will be left over is this moles on the numerator. But again, sorry, I screwed up here. This grams of copper in the answer should be moles of copper. Now, notice that the math tells you that I need to multiply 4.57 by 1 and then divide it all by 63.55. Calculator using the correct number of significant figures will tell you that the answer is 0.0719 moles. This should be moles. My apologies again. Again, I'll use 12.3 grams of potassium, try to convert that into moles. Again, I need grams to cancel, so I'm going to have the molar mass of potassium, putting the gram unit on the denominator, the mole unit on the numerator, so it'll stick around. Now the gram unit will cancel. The math tells me that I need to multiply 12.3 by 1 and then divide it all by 39.1. Again, this is a mess up. I'm very, very sorry. This should be 0.315 moles of potassium. All right, the third example, 4.57 grams of potassium using the molar mass of potassium. Gram units cancel out, only unit left is moles. The math tells you 4.57 multiplied by 1 and then all divided by 39.1. Calculator is going to help you out and tell you 0.117 moles of potassium. My bad, apologies. There's one more kind of conversion that we need to be able to do, and it's using Avogadro's number. We need to be able to convert a number of atoms into the number of moles. Now remember, Avogadro's number is defining how many particles are in 1 mole, and that's 6.022 times 10 to the 23rd. If I have 6.022 times 10 to the 23rd of anything, I have 1 mole. And so that allows us to set up a conversion factor. Regardless of what atom or molecule I'm looking at, I can define this 6.022 times 10 to the 23rd here using silver as an example. 6.022 times 10 to the 23rd silver atoms is equal to 1 mole of silver atoms. And so if I'm trying to convert from the number of atoms that I have into the number of moles, I can use Avogadro's number. I can throw that on the denominator of my conversion factor with mole on the top so that this atoms of silver will cancel out, leaving me alone with moles of silver. Moles of silver as my only unit. So, again, the math will tell me I need to multiply these two numbers and then divide by Avogadro's number, leaving me with 0.5 moles of silver. Again, here's a second example. Different numbers, 1.20 times 10 to the 8th copper atoms. I want to find out how many moles. I want to find out how many grams that is. So I have the same conversion factor. Okay, atoms. I'm going to throw that on the denominator of this conversion factor, and moles on the numerator. Okay, so now my units will be in moles of copper. However, I don't want to be in moles for my answer. I want to be in grams. So what I'm going to do is I'm going to use the molar mass. My denominator isn't popping up here on the PowerPoint, so we're full of surprises here. We have 63.55 grams, which is the molar mass of copper that you can see on your periodic table. It should be the numerator over 1 mole of copper. So that mole of copper will cancel out here, leaving me with grams of copper left over. That'd be the only unit I have, so I can carry that down here. And the math will lead me to the correct answer. 1.20 times 10 to the 8th power multiplied by 1 multiplied by 63.55, all divided by Avogadro's number. The calculator will help you out and tell you that's 1.27 times 10 to the negative 14th grams. That's a very small mass of copper. A very small mass of copper, as you can see, that's somewhere on the realm of a quarter of a mole. All right. There's a lot of conversions going on, a lot of math going on that's not intuitive here. So if you have any questions, you need to come in during AST and ask those questions. Okay, being quiet and hoping that you figure it out at a later date is not the way to approach this subject. All right, well, I hope that helped. I will see you next period.